Hi, my name is Elizabeth Terry, and I'm presenting dynamics and controls of a double pipe heat exchanger. As you know, many of you are fully aware that a double pipe heat exchanger consists of just concentric tubes. The approach in this article was really to study and to solve four nonlinear partial differential equations by linearization method. The experiment investigated using various different types of testing, such as like a step function, a sine wave function was also conducted. Their results also showed that the transfer function with variations of temperature for both streams could be approximated by the several different forms, but as the step function presented in front of you was used. So to establish kind of like our initial conditions, the experiment used a lead and lag approximation in the modeling of the double pipe heat exchanger. This analysis involved like an extraction of the successful real poles and zeros for the system transfer function, for the temperature, for the flow forcing formulated in the model, but also described. It was also described as a kind of dimensionless temperature function as a temperature function of the flow rates. So the process can be represented by partial differential equations, distributed through its parameter as far as through the system. And the experiment was studied for the double pipe heat exchanger was both also numerically and experimentally in hopes of having a strong comparison of the two for both that heat transfer and that hydrodynamic characteristics. So in this one, for the time domain fitting of the step test data, the most direct way of obtaining an empirical linear dynamic model of the process is pretty much in order to find like the initial parameters as far as like your dead time, your time constant, and your process gained. So in this experiment, even though some experiments can be performed in an open loop system, this one was tested in a closed loop system. So a step disturbance in the hot water flow rate was introduced, and then it was recorded recorded the temperature of the cold water. So as far as in a comparison of the two. So the steady state process gain, K, is equal to the ratio of the final steady state change in the output over the size of the input. So that's pretty important right there. So while the time constant is estimated from the response by using several methods, but again, that ratio is key in how they kind of identify their steady state process. And so the Bode plots were used to examine the stability of the system and evaluate the gain in the phase margin. So as one of the other things that they stated, they used a phase angle of 180 degrees, and at this frequency you would need to look at the magnitude of the plot to determine the gain of the margin in which it is gained and required to rise the magnitude of the curve. So a positive gain margin would mean that the system is stable, and of course a negative gain margin would mean the system is unstable. So the PID gain search process sometimes refers to as tuning, and for this plant they used the Ziegler-Nicholas method and process as a structure of tuning procedure. So however, like they said, not all plants you are able to use this type of tuning. So but if the performance is not acceptable, an update to the gains and kind of a reiteration of the process, like stated here, naturally MATLAB is very useful in that process. So also part of the PID controller, they used a Smith predictor, and a lot of times that's really used to just kind of remove a lot of the effects of the transport delay. And so in that first step of the design control, and also it is design is a suitable control, so when it's initially analyzed, there's no dead time. So The design is an innovative control scheme and to control the plant with that dead time. So that's why, again, that's why this was used. So on that next slide, you can kind of see how the Smith predictor as a mirror loop to the block diagram. So, and the transfer function between the two as far as a comparison. And so this is what I was talking about as far as that mirror loop of the Smith predictor, and then just that modified block diagram of the Smith predictor. So anyways, last but not least, but they use the fuzzy logic control, and it's actually something that they can generate many of the structures and provide today's scientists some new insight on how to investigate some of these problems. And it's not just in, of course, double pipe heat exchanger, but they're starting to aim it towards the development of using it in a lot more situations that are just way too complex and way too ill-defined to be analyzed by just our conventional techniques as of today. So thank you for your time, and I appreciate you listening to my video.